video is about the photoelectron spectrum. You should already be able to describe and explain what ionization energy is, but we'll review it and construct electron configurations. And by the end of this video, you should be able to compare ionization energies of various atoms and determine an element's photoelectric spectrum. Our questions of the video are: how are we so sure this SPDF thing is real? Do we have evidence? And why can we just stick to easy Bohr diagrams? So we're going to use Bohr diagrams to kind of describe what the ionization energy is, even though they're too simplistic. And ionization energy is the energy needed to remove electrons from the valence. When you do that, it creates a positive ion. As you can see the picture, sodium loses its valence electron, it becomes smaller in size, and that outer ring is gone. We need to know how much energy it takes to remove that. The second ionization energy, if you see it in a question, corresponds to removal of a second valence electron. So in the picture here, we would have to remove it from the second level here. One of these 8 would have to be removed. Will that require more energy than the first, or less energy than the first, or does it depend on the atom itself? Let's answer that. So you might remember from last year, I used to draw arrows to represent how well a proton is pulling on exterior electrons. So that's what I'm showing here. The size of the arrow hasn't changed from picture to picture, just the atom itself has changed. So as electrons are removed from an atom, the atom's nucleus can tighten the pull on fewer electrons. So notice the nucleus has not changed. The number of protons are still there, so the poles are all still there, the pull of the arrows. And because the radius is smaller, they pull on them better, right? So before I had 4 protons for every 4 electrons, now I have 4 electrons for only 3 electrons. So it shrinks in size. And therefore, if I went to steal another electron, we would have 4 poles to only 2 electrons and would shrink in size even smaller. Not to mention, you're losing the entire level in this example. So every time you remove an electron, the atom can get stronger and shrink. And it makes it harder every single time to remove a second, and then a third, and then a fourth electron. And this kind of relates to Coulombs Law. Coulombs Law says opposites attract and likes repel. So protons are positive, electrons are negative. They attract and pull on each other, as we saw on the previous slide. Protons will repel protons, and electrons will repel electrons. And the closer those particles are, the more force they'll have. So there's greater forces when the two things are close, and weaker forces when they're spread apart. This equates to an equation that we'll not use, but we'll just identify. We're not going to actually plug any numbers in. The Q's represent the charge of the particles, like positive for protons or negative for electrons. And the R represents the distance between the particles. People often confuse R with the radius or the size of the actual physical piece, the proton or electron. It is not the size or radius. It is the distance between one proton and another, or a proton and an electron. In that case, what we're saying is, if the 2 protons are both positive, that's not as good as if we have a proton that's positive and an electron that's negative. Not only that, the more of them we have, the higher the charges will be. If I have something like only 1 proton and 1 electron, the Q's will be 1. But if I have like 15 protons and 15 electrons, the charges will both be 15. So the higher the charges are, the higher this energy will be, Coulombs Law energy, or harder it will be to remove them. Also the R, if those two things are close to each other, maybe inner protons and inner electrons, their force will be closer, so there will be a greater force, right? Because the radius between them will be small. But if they're really far away, like inner protons and valence electrons, they're going to have weaker forces because that distance will be really big, which will make this energy factor very small. So using that equation again, what we're showing is hydrogen has only 1 proton pulling on 1 electron. So not only are the charges low, but the distance is probably pretty small. So they're both small. But in helium, it has 2 protons and 2 neutrons in the same radius. So this radius is the same, but the 2's increase the Q's and therefore increase the energy. And that means that it's harder to remove electrons from the helium than the hydrogen. Across a period, it makes it harder to remove electrons, because there's more pull, the arrows. And it also makes them smaller, so that means their radius is actually smaller. So lithium has added a whole other level, and let's see how that would wind up working out. The electrons in the nucleus are going to be shielded by, the protons are going to be shielded by the first row, and that means that third electron is even further away from the proton pull, and it is being protected by the inner electrons. And so in that case, it's going to be easier for a person or an atom to remove this electron, because not only is it further away from the inside, but those 2 electrons are almost distracting it, right? So again, as you go across, add more protons, it makes it harder to remove, but in this case, if those electrons are further, it actually makes it easier to remove. And as you go down groups, it gets easier and easier to remove electrons. So here's the general summary. You might want to pause and write it down. That across a period, you increase protons and therefore increase your nuclear charge or pull. And that increases the attraction for electrons and decreases the radius of the atom, or the distance r. And therefore it increases the Coulomb force and ionization energy. The energy to remove the electron increases, it makes it harder. So ionization energy increases across the table. And then down a group, as there's more energy levels created, the distance between them is so much larger, it doesn't even matter there's more protons. They're so far away that the Coulomb force is weak, and it's easier or decreases energy needed to remove the electron. So how is that going to play into the next parts? We also have to talk about binding energy. A lot of people think these are interchangeable. They're not exactly the same thing. Binding energy is also the energy required to eject an electron or remove it from the atom, but it corresponds to the sublevel in which the electron resides. So it doesn't matter, we're not talking about the first and the second and the third electron, we're talking about any electron in the valence, any electron in the 2p. Any electron, whichever one you want, in the 2s, for example. How much energy would it take to get any of them the first time? So binding energy is the first time removed electron from that level. In that case, we should talk also about photoelectric spectrum, photoelectric effect. So how can we remove the electron? What we could do is force light onto the surface, and when the light hits the surface, if it's strong enough, like maybe more like gamma rays or X-rays, it will eject the electron from the top, and that's why we can see things. If the light rays are too weak, or we're talking about something like radio waves, they will not be strong enough to eject the electrons, and so you will not have an electron emission. The reason we need to talk about that is because that photoelectric effect is how we use photoelectric spectrums. So this device shoots a laser at the top of a sample. The sample ejects this electron based on the ionization energy or binding energy, and the electron goes through the device. The scanner analyzes at what energy the electron is ejected and gives it a value, and we come up with graphs. So for the hydrogen, it only has one electron. The graph is how many electrons it has, which is on the y-axis, and only has one, versus how much energy it took to eject it. So we only have one peak because there's only one electron. The energy is written from high to low. So the higher the energy is actually over on the left side, this 0 is for the y-axis, and it gets lower as you go across. Helium looks really similar because it only has one peak because both the electrons are in the same area. They're both in 1s orbitals. So both of them will take, it doesn't matter if you take electron A or B, they'll still, if you take it the first time, it will be the same energy. So it has one peak, but this peak should be higher in value on the y-axis because there's actually two electrons that are doing that. This might be easier if we look at a more complex, but not super crazy, element, right? Like beryllium. Beryllium's configuration is 1s2, 2s2. So that means these peaks show the two electrons in the s and two electrons in the s. There are two peaks though because it's easier to remove from the 2s, which is lower energy, and it's harder to remove from the inner electrons, which is higher energy. Remember, this axis is backwards from high to low. So these peaks are the same height because they have the same electrons, but there are different energies. Even better, carbon. Carbon has electrons in the 1s, the 2s, and the 2p orbitals. And so it doesn't matter which electron we're taking it from. If you take it from 2p, it takes less energy. So this is your 2p. If you take it from 2s, it takes more energy, but there are two electrons there that you could take. And if you take it from 1s, it takes the most energy, and again, there's two electrons. So again, these peaks are the same. Will they always be the same height? No. So if we look at this one, we're trying to figure out what element it is, we might want to see what peaks they might represent. So this has two electrons, and it's the hardest to remove. That would be the 1s2 sublevel, always the 1s2. Then if you have more electrons, it'll be easier to remove, right? So less energy to remove it, but it's also the same height, because that was a 2s2. All of a sudden, you have this huge peak. This huge peak represents 6. There are 6 electrons in the huge peak, which must mean the p block. I think this is showing you that the SPD thing is like real, right? This block would be 3s2 because it's the same height, 2 electrons, but it's much easier to remove because it's getting further from the nucleus. Any electron in that block, if we took it, how much energy would it take? And last, our last peak. This peak, I don't know if it's clear on here, but it would clear on a test, is at a 5. Oh, I wrote 4. It's at a 4 apparently. Okay. So if it's at 3p4, which might have been labeled for you a little bit better, clearer on a test, that means that if it lined up to 4 here, that means there's only 4 electrons in the p block. If you look up what that is on the reference table, that's sulfur. So you can actually use PES diagrams to identify what the substance is, which is really neat. We just did it backwards. We used PES to verify that SPDF was a real thing, which is pretty nice. Now, why couldn't we just use Bohr? Why do we use SPDF? Because if you look at the Bohr diagram for carbon, it looks like there should only be 2 peaks. There would be a peak for the first row of electrons, and there would be a peak for the second row of electrons. But what we're seeing is 3 separate peaks. Why? Because this is corresponding to the 2s electrons in the first orbital, and this is corresponding to the 2s and the 2p, which means that this is not clear enough. It's showing 4 electrons that have the same energy, when in fact, it should be 2 electrons that have s energy and 2 electrons that have p energy. So this is not really clear enough for us. We needed to do the SPDF. So at this point, hopefully you can compare ionization energies and maybe even binding energies and determine an element's photoelectric spectrum.